Hello, this is Mr. Collier, and today we're going to start integrating using trig substitution. So here we have three integrals that require trig substitution, and we're going to look at some patterns of these numbers and or these integrals and why we have to use trig substitution rather than something else like u substitution. Okay, first of all, notice in each expression we do have a radical. Okay, so we have a square root symbol here, and here we have a power of half here, so that's also going to be a square root. So one thing that's in common with these trig substitutions, you'll often see square roots in them. Okay, and also notice that we have x squared in each case, and these will not be, you'll not be able to do your substitution on these because we don't have, for example, we don't have, if we let x squared or u equals x squared, then du equals 2x, and we don't have an x in here at all, so we can't use u substitution. If there was an x or a 2x in the numerator here, we could do u substitution, but we don't have that, so u substitution is not possible. Okay, so in each of these cases we have a radical, and we have an x squared inside the radical, and another constant term. So when we have that situation, we can use trig substitution. Okay, now each of these look very similar, but they're actually three different types. If you look at this one, we have a constant and an x squared term, and we can rewrite it like 4 squared minus x squared. Okay, so we can rewrite it like that. So it's of the form a constant squared minus x squared. So that's one type of trig substitution. And the next example we have, well, we can rewrite this as 5x squared minus 1 squared. Okay, so we have that. So this is of the form x squared minus a constant squared, where in this case x is actually equal to 5x. And in the last example here we have well, 5 is not a perfect square number, but we could write it as root 5. So we have root 5x squared plus 2 squared, which is of the form x squared plus a squared. Now there's only three forms because, well, a squared minus x squared is not the same as x squared minus a squared. But if we switch these around to a squared plus x squared, then it would be exactly the same. So there's three types of trig substitutions you could get. And these trig substitutions are all going to come down to using a couple of trig identities. Okay, a couple of important trig identities are, well, one of the most important is sine squared plus cosine squared. Let's put in a theta here, equals 1. Okay, that's important. And this can be rewritten as sine squared, actually 1 minus sine squared equals cosine squared. Okay. And we have another important trig ratio or trig identity that is 1 plus tan squared of theta equals secant squared theta. Alright, and that can also be written as, can rewrite that as tan squared theta equals secant squared theta. Okay, so what we're going to do in trig substitution is you could take one of these identities. Well, I think I missed something here. It's supposed to be a minus 1 there. So what we can do is we can use these trig identities, these three here, to do some trig substitutions. So let's take a look at these more closely and see how they match three different types that I have up here. Notice in here, the first one, we have a constant minus the x term. So if we look at which one corresponds, well, here we have constant plus a tan squared, and here we have a constant minus a sine squared. So that's how you tell what type it is. We look at this trig ratio here. we can change this to look more like 1 minus sine squared, and then it will become cosine squared. And then because of the square root, the cosine squared will cancel. And we'll have a nice little trig function inside of here that we'll be able to integrate. Okay, so this one here, we'll use this trig identity, 1 minus sine squared theta equals cosine squared theta. Okay, so in this case, notice that the x corresponds to the sine theta here. So in this case, we do a substitution. Let x equal sine theta. So that's the substitution we're going to do, and that'll all work out. I'll show you that in the next video. Okay, so look at the next one. We have a x term and an a term. Okay, so in this case, if we look at our functions here, we have over here we have a trig function squared minus a constant. So that's going to be just like that one looks. Okay, so notice that we have x squared minus a squared corresponds to secant squared minus 1. So that's the one we're going to use there. We're going to use the tan squared theta equals secant squared theta minus 1. And we're going to let, okay, notice this corresponds to this. So we're going to, when we do the substitution, we're going to let x equals secant theta. Okay, in the last type, when we have the addition, we have the x squared plus a squared. We're going to, well, that's going to correspond to this one right here. We have a constant plus tan squared. So that's going to be like tan squared theta plus 1 equals secant squared theta. So what's going to happen? We're going to let x equals tan theta, and then we're going to magically rearrange this, and we'll get a secant squared theta, which will cancel with the square root. So it'll be a much easier function to deal with when we do the substitution. Okay, so all the details of each of these 3 problems will be fully explained, and the whole solution will be fully worked out in the next few videos.